And I think it's time to start now. So it's my pleasure to introduce Kateryna Pozharska from Academy of Science, Ukraine Academy of Science in Kiev. She belongs to the group of Anatoly Romaniuk. No, Victor Romaniuk.
Anatoly Romaniuk, yes.
Anatoly, sorry, yeah. She visited our faculty in the pre-corona times. This is where we met and did some work together, where she's going to tell us about today. So please start your talk. So the stage is yours.
Okay, first of all, I want to thank organizers for this great event, especially Tino Ulrich and Volodymyr Temlyakov, and for their kind invitation. And I want to tell you our recent results with Tino Ulrich about sampling recovery of multivariate functions in the uniform norm. So I start with some notation. And we have a function that goes from a subset of Rd to C. And we know function values at some points x1 till xn. Our aim is to reconstruct this function from samples. And the main feature of this approach is that our construction operator should work for a class of functions simultaneously. That is, in contrast to Monte Carlo methods or some sparse grid techniques, we want that the sampling error is good for each function from our class, using the same sampling recovery operator. And we will work in the framework of reproducing kernel Hilbert spaces h of k with bounded kernel k. And why do we need this boundedness of the kernel? Because we will control the worst case error in L-infinity norm. And the boundedness of the kernel ensures a compact embedding of our h of k into L-infinity. And further, we discuss the power of standard information in the uniform norm. And our results are more or less general. So then we give concrete examples of Sublev type spaces, and we were able to write asymptotic and also pre-asymptotic results for this concrete classes of functions. And just to recall the definitions of worst case recovery, about the minimal worst case errors that can be achieved using linear information and standard information. It's if our h of k is a Hilbert space, we will call this an approximation numbers. And if this target space f equals to L2, yes, then our approximation numbers coincide with singular numbers of the corresponding embeddings. And here the question of reasonable assumptions arises to ensure the polynomial order of decay of these quantities an and gn, that is the supremum over q, such that our an and gn are of order n to the minus q. And on the next slide, you have just an announcement of our main results. So the strict formulation will be later. But what we have done, sorry, what is going now? Can I share?
I still see your screen, but
Vitaly.
But without the presentation, maybe you should.
Yes. Okay. Now it works, sorry. So if we have a polynomial order of, it seems that Vitaly Nayorov is manipulating with my screen, sorry. Can you?
Wait.
Okay, I will start sharing. Yes. And so if we assume that our singular numbers have a polynomial order of decay, then the power of standard information when we use linear information and measure the error in L2 norm equals to pi. When moving to L infinity setting, yes, one loses 1/2 in the optimal order. It's for linear information, and it was proved by Kuhl, Vasilkovsky, and Pozharska. But here we need some additional assumptions on the function n of k. It will be introduced later. It is a supremum over the so-called Christoffel function. And as to the standard information, the power of standard information, up to now only the bound for this Q standard infinity was known. It was also established by Kuhl, Vasilkovsky, and Pozharska. So the upper bound is pi minus 1/2, but the lower bound was also expressed in terms of pi. But we prove that we really have this equality here. So under the following assumptions, the power of standard information in the uniform norm equals to so the power of linear information. And moreover, we proved the following estimate for sampling numbers and approximation numbers. The both sides have this identical operator that goes to L infinity. And I want to say that the recent breakthrough was made by David Crick and Mario Urlich in their recent paper, this part 1, in establishing a connection between sampling numbers and approximation numbers in L2. And for further refinements, we refer to the following names. I will comment more further on the results, but we dealt with L infinity in both sides. So L infinity for sampling numbers and for approximation numbers. Okay, and I think I will move further. So we introduce L2 and L infinity spaces. And here for L infinity, we don't need essential supremum, just supremum. And as we deal with reproducing kernel Hilbert spaces, then for each f from our Hilbert space, the following reproducing property holds. And we assume the boundness of the kernel K to ensure compact embedding into L infinity. Know that if you consider the embeddings into L2, then it is sufficient to impose a condition for a finite trace condition, because it ensures the embedding into L2, compact embedding, and that our singular numbers, sigma n, are square summable under this condition 4. And we'll incorporate spectral properties of our embedding. So our lambda n and sigma n are eigenvalues and singular values that are rearranged in the non-increasing order. So also we choose the respective singular functions, right and left, this en star and eta n. And in general, our system En star is not a basis in H of k, so it is only orthonormal system. But there are conditions that are connected to so-called Mercer's theorem that ensure that our system is a basis in H of k. And namely, if we assume that our kernel is bounded and continuous on a compact domain D, and also our measure rho D is a finite, is a Borel measure with full support on D, then our system En is a basis in H of k. There are papers that don't need our system to be orthonormal system, maybe orthonormal basis. Maybe Tim Urlich will tell us more about the situation, but in L infinity setting, we do need this assumption. So we will work with Mercer kernels, and our recovery algorithm is built on the least squares algorithm. It was used by David Crick, Mario Urlich, and then Lutz Martino Urlich and Tony Walker got worst case error guarantees with high probability for such kind of algorithms in L2 space. But we will use weighted least squares algorithm. So instead of our samples, yes, we'll use weighted samples. So we introduce some additional weight function, this rho m. It will be defined on the next slide. And also our matrix L will consist not of eta, but of eta divided by the square root of this weight function. Why do we need this weight function and how it looks like? David Crick and Mario Urlich introduced rho m in the form 8. One can take another form of this function, 9, where instead of this second term, we have just 1/2. This type of function was implicitly used by Cohen Migliorati and Vladimir Temnikov. And in several situations, it doesn't make difference which function to have to consider, but sometimes it makes a difference even in a univariate case. So it makes differences in the main order of convergence of algorithms. And we draw our points with respect to this tailored measure, rho m, rho d. So rho d is our initial measure, and we multiply it by our weight. Why do we need some kind of weight function? Just a quick overview without details. So we want to control the worst case error achieved by our weighted least squares algorithm. So to estimate the first term, f minus projection, we introduce this n of m. It's a supremum over so-called Christoffel function. It is implicitly used in literature in several situations. So here we don't need this weight function, but when moving to the second term, yes, we want to control the L2 error, L2 norm of the coefficients. And in view of our algorithm, it means that we want to control spectral norm of the Murray-Penrose inverse and L2 norm of our weighted weighted G. So it's f minus projection divided by weight function. And as to the spectral norm of this Murray-Penrose inverse, we can use the result by Nicholas Nagel, Martin Schäfer, and Tino Urlich. I will not get into details about the history of this result. So there are a lot of previous results that are connected to this result, but maybe Tino Urlich will comment more on Friday. And just to say that here m is related to n, so m shouldn't be much bigger than n. And introducing our weight function, we can control this weighted n in terms of m. So we don't need to compare more n of m and n, but just m and n, which is good for us. And then I want to tell you that not usually we need this weight function. So there are cases when our system eta is uniformly bounded by some constant. It holds for a trigonometric system, it is uniformly bounded by 1. So we have n of m of order m, and we don't need this weight function. So we can use simple least squares algorithm without this rho m. But in general, we do need this weight function. And as to the second term, I mean this one, to estimate L2 norm of our G, we need concentration inequalities for infinite matrices, because our f minus b m minus 1 is infinite. So we can use result by Moritz Moller and Tino Ulrich, which is an improvement of previous research by Oliveira, Trop, and there were a lot of people working in this field. So we take our yj as follows, and our weight function ensures this condition, so that the norm of yj is bounded. And as I told you, if we have a kernel with finite trace, our singular numbers are square summable, so this sum is finite, and it is good for us. On the slide, you can see our general results for reproducing kernel hybrid spaces. And here our ρd is a finite Borel measure with full support, not necessarily probability measure, because if we have this ρm, our ρm d ρd becomes a probability measure on d. And here we have log m over sampling. And this estimates hold with high probability, namely here we have 1 minus 3 multiplied on n to 1 minus r. And this constants can be estimated precisely, so C1, C2, and C3. And here you see their values. For arbitrary orthonormal system, we use this weighted least squares, and for uniformly bounded systems, we use plain least squares algorithm. And if our ρd is such that for the supremum over Christoffel function, the following relation holds, then our n of m and m cancels, and we have just sum over squares of singular numbers. And we can use here the result by Kobes-Kuhn-Sicken, who estimated approximation numbers, but here there are approximation numbers in L infinity via the sums of singular numbers, and get the result 15. But I want to show you the difference between our choice of weight function. So if you take ρm as the following form, yes, you derive to our upper bound. And if you have 1/2%.
Excuse me, Katja. Could you please mute your microphone? Or Elena, can you care about muting the microphones of all speakers? I think this is possible from the host. Okay.
Okay, I can continue. Yes?
Yes, please continue.
Thank you. So if you take instead of this big second term 1/2, you get additional this n of 4k over k in the upper bound. So it doesn't make difference if our n of k has the order k, but in some situations it causes a difference in the main rate. But just to note that one can also use the plain algorithm, but we should compare here not m and n, but our supremum over Christoffel function, and we get the bound 16. So a few words about another approach. It is based on the so-called Weaver's downsampling procedure, and I think that Tino Ulrich will tell us more on Friday on this algorithm. It was based on the proof of Weaver's conjecture by Nitzan, Olewski, Ulianowski. in 2016, and this kind of algorithm is widely used by Vladimir Temlyakov for Marcinkevich discretization problems, and Irina Limona will also give us a talk on their recent research with Vladimir Temlyakov. So just a few words about this algorithm. We want to shrink our matrix and to use, instead of m log m samples, just m. The order samples, number of samples of order m. And here we can use the following theorem for frames. So we can restrict ourselves in considering the subframe, where the cardinality of J is less or equal C1 multiplied on M. And so we get the following results for sampling numbers. The first one refers to this log M oversampling, and the second refers to this Weaver's downsampling procedure. And here we get additional log, but it can help us in several situations, in particular for Sublev type spaces. And if we have here that n of k is of the order k, then the formula 17 holds. You have already seen it, seen this formula on my first slide. So sampling numbers behave almost the same as approximation numbers in L infinity. So we just have the square root of log m. But I want to note that this approach works for L infinity, and our least squares algorithm was tailored with respect to L2, to the space L2, to the properties of this L2 space. There is a question if we can make similar similar results for LQ space, but it seems that it doesn't hold for LQ, because we may write some results, some estimates from above for sampling numbers, but they will be too coarse. So this weighted least squares algorithm will not work well for LQ setting. And few words about the comparison of sampling and Kolmogorov numbers. So the recent breakthrough was made by David Crick and Maro Ulrich by establishing the connection between sampling numbers and singular numbers in L2. They used log m oversampling. So in this sum, you have m over log m. And for the refinement, I refer to the following papers. They also used log m oversampling, but in the paper by Nicholas Nagel, Martin Schäfer, and Tino Ulrich, they prove that we need just m in this sum. So they used this Weaver's downsampling procedure for proving their results. Also, Vladimir Temlyakov proves the following bound for sampling numbers in L2 and Kolmogorov numbers in L infinity. And we try to get the similar results when we have L infinity in both sides. So we derive to the following estimates. The first one is without our downsampling procedure, and the second one is with it. And this n is nothing else as our supremum over Christoffel function that was defined earlier. But for these results, we need our optimal subspace for Kolmogorov width. So if we know the subspace, we can estimate our sampling numbers in terms of Kolmogorov numbers. But in general, the estimates for Kolmogorov widths are non-constructive, and one cannot say in which subspace the estimate for dm is achieved. So in general, we don't know how the square root of n behaves. but it can be of help. I will tell you how it works in this L2 L infinity setting. So there are recent results by Vladimir Temlyakov and Tina Ulrich for approximative characteristics in the case of small smoothness. And this case is in this case, the crucial point is that our sigma n are not square summable. So one cannot use the first formula, because here is the sum of sigma n squared. But one may use a second one for this reason. And so if we will be able to estimate our square root of n, then we can write down estimates for singular numbers in L infinity via the estimates for Kolmogorov-Width in L infinity. But it's an open question up to now, I think. So I move to the next topic. It's the power of standard information. And here are the definitions of our power of the optimal order of convergence of algorithms that use linear information and standard information. And you have already seen these assumptions on our first slide. These assumptions were considered earlier by Ku, Vasilikovsky, Wozniakovsky, but instead of assumption 1, they assumed that the system eta is uniformly L infinity bounded. But it's nothing else than our assumption 1 in the case when u equals 1. So it was known, so for linear information in L2 and L infinity, the bounds were known. But for standard information in L infinity, only this bound was known. So the upper bound is sharp, but the lower bound was in terms of pi. And we managed to show that the power of standard information in the uniform norm under these assumptions, 1 prime and 2, equals to this Q linear infinity. And if we assume a weaker assumption, yes, 1, we can show that our Q standard infinity is at least pi minus u over 2. So we are not able to prove the upper bound up to now, but at least it is greater or equal than pi minus u over 2. And now I want to give you concrete examples of Sublev type spaces. So here we have the space HW with a weight function W of k, where ck are Fourier coefficients of f with respect to our trigonometric system. And Kubus-Kuhn-Siekel established their conditions on the weights W of k that ensure the compact embedding of our space into L infinity. Even more, they showed the equivalent conditions for embeddings of the space into the Wiener algebra and the space of continuous functions, but we need here only the embeddings into L infinity. But we will look at this space from the point of view of reproducing kernel hybrid space. And the respective kernel takes the form 19. Our eta n is a system of exponent that is rearranged in the order of importance, that is in the non-increasing order of our weights. Yes. And we introduce this frequency set IR and its cardiality M of R. For this general weights W that satisfy the following condition, we can write estimate 20 for a log M over sampling. And now, so the corresponding estimate for sampling numbers takes the following form, and the second term corresponds to this Weaver's downsampling procedure. We have this additional square root of log. here. And just to know that for periodic functions, in L infinity case, similar estimates were established by Lutz Kammermer, and this paper improves the previous results by Lutz Kammermer and Tony Walker. They dealt with rank 1 lattices that allow for fast Fourier transform algorithms, but they have here additional log that we showed is not really needed in this periodic situation. And now we will take particular weights W. So here we had like general W, and now we take it of the particular form. So this class is S sharp and S plus, and also S star classes were introduced by Thomas Kuhn, Winfried Zickel, and Tino Ulrich in their paper of 2015, where they got asymptotic and pre-asymptotic results for approximation numbers. But now that they are equivalent up to constants that can depend on some parameters from the asymptotic point of view. So this estimate was known for a long time. And using our results, we can write down the asymptotic estimates for our plane least squares algorithm. Why plane? Because our trigonometric system is uniformly bounded by 1. So we don't need this weighted algorithm. And it refers to log oversampling. Also, we can use downsampling procedure. So we can derive to the estimate 24. We have here additional square root of log, but the estimate 24 is better than 23 for s greater than 1, because we have here oversampling. So if we put here n, we need to divide m over log m. So our estimate 24 is much more convenient for sufficiently smooth function classes. And as to known results, so Vladimir Temnyakov got the asymptotic estimate for some sparse grids. It is better when we look at the power of logarithm, but we managed to get also pre-asymptotic results. So we can write down the constants and their d-dependence. So we can use pre-asymptotic results for singular numbers from the paper by Kuhn. And also we can deal with another norms, like we can use the result by Kuhn, Zickel, Ulrich for a plus norm, yes, and also put them here and write down the respective pre-asymptotic estimates. And just to know that, if you look at our general results, we have here n over m. For a trigonometric system, it cancels, but in the next example, you will see that it may influence in some, in the case when our n of m is not of order m. So now we consider classes h of ks, which appear from the second order differential operator in connection with L2 normalized Legendre polynomials. And here I want to mention the book by Nevai, where the growth of our n of m was given for the spaces of polynomials of degree n for different Jacobi weight parameters. So if in case of Legendre polynomials, alpha equals beta equals 1 for the Jacobi weight, and our n of m is of order m squared. So we get the following bound for sampling numbers. And about the known results, so for polynomial operators that use on Gauss points, yes, for L2 setting, it was the result by Bernardi and Mede was known. It was optimal in the main rate. but the power of logarithm is not optimal. Further, Lutzke, Martin Orlich, and Tony Walker got worst-case error guarantees with high probability for some weighted least squares algorithms, and they improved the estimate of Bernardi and Madej in the logarithmic order. And here we have the same main order, but I want to show you the difference between the results when we use this weight function rho m and rho m prime. So if we have this second term of the following form, we get minus s plus 1. But if we take just 1/2, then our estimate is worse even in the optimal, even in the main order. We even may use plain least squares algorithm, so without our weight function, and this estimate for plain algorithm is sometimes better than estimate 29 for weighted algorithm. It holds for small s, like s between 1 and 2, but this red one are never better than the blue one. So our rho m of the form 28 is the best for this setting. And just 1 minute on another example built on Chebyshev polynomials. So it is a non-periodic example. And here we use Chebyshev measure, yes, and define multivariate Chebyshev polynomials in the following way. And note that here our k, yes, so the components of k are non-negative integer. And just to show you the realizations of random nodes with respect to the Chebyshev measure, so you see more points near the boundary. And so the respective reproduction kernel takes the form 30. We rearrange our singular numbers in the non-increasing order and introduce our set H of L. So it is the set of such k that correspond to the biggest singular values, sigma. And we want to get the worst case error guarantees for these non-periodic classes where we don't know the behavior of the sigma n. So we make a trick. We introduce the sigma n pi where we allow our components of vector k to be integer. And we can use the results for so-called mirrored sets. So just for illustration, in two-dimensional case, if our downward closed set is bounded by some hyperbolas, as in our case, yes, we have some points, and we mirror this set. So we allow all sign changes of our of the components of vector k. And the cardiality of this mirrored set is not always like 2 to the d multiplied on the cardiality of our sets, because some points coincide with the mirrored one. So we don't need to mirror each point. For example, that one that belongs to the axis, or there are much more such points, and we can use the result by Schiffer, Cohen, Migliorati, Nobilem, and Tempone. 31, yes. This bound appeared earlier in the second indicated paper. And so introducing this additional rho pi n, we can write down worst case error guarantees with high probability of non-periodic function classes built on our Chebyshev system of polynomials via this mirrored sigma pi m. And here we can use, like, for specific examples, for specific weights, I mean sharp norm, plus norm, or star norm, we have the estimates for singular numbers of corresponding periodic classes. and we just put them here, and this constant C1 and C2 are can be explicitly given, so we know them, and there are d-dependence, and we can write down here pre-asymptotic and asymptotic results as well. So this part of our research is under construction, so I will not give you like sharp estimates and the view of the constants, but this was the idea. Okay, I think it's all for today. Thank you very much for your attention.
So thank you very much, Kateryna, for your nice talk. Are there any questions or comments?
Maybe I have one. So someone should
Please.
maybe ask a question. So thanks again for the nice talk. So could you please show the examples again? I think only 3 slides before. So
Okay, you mean a periodic one or?
The one where you showed that the weighted least squares was better than the other one.
Okay.
And the example. Oh no, I think we are too far away. It was a Bernardi Massai or something example.
Okay, okay.
This was it. This one? Sure. No. No, it was.
I think this one, yes.
Somewhere, yes, exactly, exactly. This one is it.
Sorry.
So, do you know? So that's only an upper bound, clearly, and so it's maybe not completely clear that they are really worse. But do you have any kind of lower bound that shows that at least the last one, where you lose this 1/2, can really not work? Or let me maybe be precise on my question, because it cannot be because of the construction of the point sets, right? So most of the results are with high probability, and which means even if you change the density a little bit, most likely you will still get a good point set, not with high probability, but at least with some positive probability, right? So somehow the algorithm is also a source of destroying the weight. So do you know anything about that, or is it still not clear?
So as far as I know, so in L2 setting, we can compare the results for this like algorithms that use points drawn with respect to some measure, yes, with some deterministic algorithms by Bernardi and Madej and some others, but in L infinity we are not aware of some deterministic results. So it is, I think that we cannot like compare our with some other results. Yeah.
Okay, thank you.
Sorry.
Are there further questions? So maybe I have a comment. On the last slides, you showed this Chebyshev stuff. Actually, why it is useful to consider that? Because this setting on the first glance, it seems to be a bit artificial. So that you have here this weighted L2 space in the error norm, and this space with the Chebyshev measure and so on. Why is it useful to consider this situation? What implications does that have?
Okay, these non-periodic classes, the classes of functions is h of kw, they are greater than periodic counterparts. So, our h of kw, our periodic classes are embedded into our non-periodic. Without, if we consider periodic classes without periodic continuation. So our estimates work also for periodic classes.
What I mean is actually that, probably you said it, that this space of this with this particular Chebyshev curve is larger than the non-periodic case, right?
Yes, yes.
So in that sense, worst case estimates with respect to that larger class give you for free estimates for the classical non-periodic Sobolev spaces, right? So in that sense, these estimates are useful for the non-periodic setting, right? But you mentioned it in the talk somewhere, but maybe it was a bit.
Thank you for this comment.
Are there further questions? Okay, time slot is finished, I would say. I mean, if you have further questions or other discussion going on, we can do that unofficially in the break. So the morning session is over. Thanks again, Kateryna, and thanks all the other speakers, Jan and Alexei, for their very beautiful talks. We will meet again in the afternoon, 3 o'clock Moscow time, with the talk by Erich Nowak, which is chaired by Vladimir. He will then join us since his time zone will permit it. So, and then afterwards, Vladimir Temelkov will give a talk on discretization in LP. So that's the afternoon. Sorry? Somebody has a question?
No.
Yeah, so we will meet again at 3 o'clock Moscow time, which is 2 o'clock European time. Are there any questions to the program or to other things? Maybe we can do that now before going into a lunch break. So hope to see you all again in the afternoon. And then I would say we go to lunch break if there is no further discussion.
So I have another one, Tino. Maybe we can ask some other, so together with Kateryna, if possible, some only two minutes or so. But we don't need to record that and stuff like that, right? Is it fine for you, or?
Should we meet somewhere else? I don't know.
I have no problem to do it here, really. I'm completely fine.
We can discuss here, yeah.
Okay, it was really just to the question I've...
Okay, thank you. Goodbye.
The other ones, please turn down their microphone. The host still has opened its microphone. Whoever it is, please, could you turn it off?
Turn off, okay.
Yep.
Yeah.
Or not. Okay, now, great. So Kateryna, it was just again to the question I've already asked. Did you try to find some, structural differences between the algorithms, right? Because your result that you showed in the upper bound most likely boils down to the construction of a point set, right? As I said, we all prove the results with high probability and stuff like that. So, okay, but assume you are taking the non-weighted least squares, right? But take a good point set. You know that there is a good point set, an almost optimal point set, which is maybe constructed by a weighted whatever, right? But now you have this optimal